Today we begin our discussion of correlation coefficients. Correlation is a statistical technique used when we have two variables that are both measured at the continuous level. Consistent with how we've taught the course, we've been teaching you that different statistical techniques are associated with different kinds of data. The more numerical or quantitative data contained in your variables, the more sophisticated statistical analyses you can do. In this particular case, we're dealing with two variables. Typically, we'd identify one as the independent variable and one as the dependent variable, both of which are quantitative or continuous. If you have data that are measured as where both variables are continuous variables, we can calculate a measure of association and talk about the strength of the relationship between the two variables, discuss how they co-vary or how they vary together by calculating a statistic called Pearson's correlation coefficient, or Pearson's R. Pearson's R is a pretty good statistic to know about. It has a couple of very positive characteristics. Number one, it's a dimensionless statistic, and by that I mean regardless of how we measure things, it will always produce a value between -1 and 1. And it indicates both the direction of the relationship, negative or positive, as well as the degree of the relationship, how far away it is from 0, close to the extremes of either 1 or -1. A second positive characteristic of a correlation coefficient is that it's invariant to changes in the scale of the variables. And what I mean by that is, regardless of how we measure the things going into the correlation coefficient, it'll always reduce the scale to something consistent using a z-score factor. Now, if we measure something in terms of miles or kilometers, we'd like to be able to correlate that measure of distance with another variable. For example, how long it takes people to drive to campus or to get to campus. If we use miles versus kilometers and they produced a different correlation coefficient, the statistic wouldn't be as useful to us. But because Pearson's correlation coefficient is invariant to changes in the scale of the variables, regardless of how we measure the distance, miles or kilometers, it'll produce the same correlation coefficient. Finally, Pearson's correlation coefficient isn't affected by sample size. We could correlate 10 cases or 100 cases, or 10,000 cases, and again, our statistic will always be between -1 and 1. This doesn't hold for the test of significance that we'll talk about later. Like our other test of significance, it is affected by the sample size. Bigger sample sizes produce smaller standard errors, and smaller standard errors are associated with larger t-statistics and a greater likelihood of rejecting the null hypothesis. Not everything's perfect with correlation coefficients. For example, correlation coefficients do a pretty good job of helping us identify and measure linear relationships, but they don't do a very good job with curvilinear relationships. So anytime we see a relationship between two variables that changes over the measurement of those variables, nonlinear measurements, then correlation coefficient can be misleading. It could either understate or overstate the nature of the relationship. Correlation coefficients are also sensitive to extreme cases. And by that I mean, when we tear into this statistic, you're going to see that part of how we define or calculate the statistic is by measuring the deviations of scores from means. Then the further away from the mean a score is, the more influence it has on the statistic, the more it contributes to this statistic. So cases that are extreme are more influential and therefore can sometimes influence our statistic and make it overestimate or underestimate the true relationship. And finally, and you've probably heard this in a number of courses, that correlation is not causation. When we start talking about causal relationships, correlation is a necessary but not sufficient condition to establish causality. Unfortunately, for most of the social science data that we work with, trying to establish causality is very difficult because we don't have the ability to establish the temporal nature of a relationship. This is very different from experimental design, where we control when things are introduced into our experiment. But for most of us who are using general social survey kinds of data, we can talk about correlation, but we're not able to say that that's a causative factor. Here's an example of a publication-ready table showing a correlation matrix. It's got some of our old friends here in terms of variables. We're looking at the correlations between sexual frequency, age, and here we have some new variables: sociability, measured by how frequently people go to bars, how frequently they visit relatives, how frequently they visit friends, and how frequently they visit people in their community. Remember, the correlation coefficients will always be between -1 and 1, and values closer to 1 imply stronger correlation. Values closer to -1 imply stronger correlations. I've also included the means, standard deviations, and sample size at the bottom of the table for some additional descriptive information. Finally, I'm only presenting half the correlations. That is, if we correlate age with sexual frequency, we get the same result as if we correlated sexual frequency with age. So we're only showing half the results. Finally, last thing you can see here is that if you look at the table closely, you'll see there's places in the table where there are asterisks. The asterisks are indicative of statistical significance, and they indicate at what alpha value we would reject the null. At the bottom of the table, I give a guideline to this. For example, 1 asterisk means that we would reject the null with alpha equal to 0.05, 2 asterisks with alpha equal to 0.01, and 3 asterisks with alpha equal to 0.001. So even though we don't know how to calculate the test of significance yet, which we'll learn a bit later, we know that there is one. We could look at this table and immediately conclude, for example, that the relationship between age and sexual frequency is negative. The implication here being that as people age, sexual frequency declines, and that relationship is statistically significant. We can also begin discussing the magnitude of this effect, although with a correlation coefficient it's sometimes a little difficult because we've got it measured in this dimensionless statistic, -1 to 1, and it doesn't lend itself well to saying, well, how many times per year on average does sexual frequency decrease with age? When we look at correlation coefficients, I advocate visualizing the data, and we do that with a scatter plot. Scatter plots can be overly complicated with too much data on them if we plot every point. For example, if we look at the relationship between sexual frequency and age, we would have to plot over 1,700 points on that plot. On the x-axis, we would have age, and on the y-axis, we'd have sexual frequency. To simplify that plot but still show the general relationship, I've calculated age groups, 18 to 24, 25 to 29, 30 to 34, and so forth. And for each of those age groups, I've calculated the average sexual frequency and then plotted those points and connected them with a line to highlight the relationship. This isn't really the same as looking at the true relationship or the true scatter plot of these two measures. It's more of a stylized version of it, but reduces the complexity by plotting way fewer points and allows us to see the general trend. I'd note 2 things about this. First of all, you can see that the direction is negative. Older people are associated with lower sexual frequency. Older age groups, lower sexual frequency. And on the other hand, this is not totally a linear relationship. There's a brief uptick among younger people where the sexual frequency increases for a couple of the age groups before it starts sort of that lifelong decline by age group. That nonlinearity could make our statistic a bit problematic, but in this case, I've calculated the correlation coefficient excluding those younger groups and including them, and the correlation coefficient remains very close to -0.36. So I'm not worried about the curvilinearity in this particular relationship. Let's look at another variable. We can look at the relationship between sexual frequency and sociability measured as how frequently people go to bars and taverns. Here we see a correlation coefficient of 0.20 and it's statistically significant. So one interpretation of this is, first, the relationship is statistically significant and it indicates that the more frequently people go to bars, they report on average greater sexual frequency. When we look at the graph down on the lower right, we can see that as people report going out to bars or taverns more frequently, there does appear to be an increase in average sexual frequency that they report, up until the group that goes out to bars almost daily. I leave it up to you to figure out why there might be a decrease in sexual frequency for people who go to bars on a daily basis, but this is a strong curvilinear relationship, and it's an important part of the story. First of all, our correlation coefficient might be underestimating this relationship because of that big turn at the end at the higher values of frequency of going to bars. And number two, if we were describing the relationship to people, it would be important to note that while the general trend is linear and positive, there is an exception for people who go to bars very frequently, an important addition to our story about the relationship of these two variables. When we look at correlation coefficients, we're really talking about whether two variables are related to each other. If there's no relationship, then our values of x are in essence randomly paired with values of y. And they would look like a big scatter plot, kind of like a chocolate chip cookie, kind of scattered randomly across the x and y axis in a scatter plot. If we have a positive correlation between two variables, then typically large values of x are paired with large values of y, small values of x are paired with small values of y, and averages near the value of x are paired with average values of y. A negative relationship, on the other hand, is a little bit different. Here we typically see that large values of x are paired with small values of y, small values of x are paired with large values of y, and like the positive correlation, average values of x are paired with average values of y. A scatter plot helps us see these kinds of relationships. Here's two scatter plots based on data similar to the General Social Survey, but international data. I'm looking at two particular variables. One is the percent of a country willing to pay higher prices in order to protect the environment. The other is the percent of a country, the percentage of people in a country that view nature and the environment as something sacred. Those are our two dependent variables. Our independent variable here is gross national product per capita. So for example, when we look at the graphic on the lower left, we can see that as gross national product increases, there's a general increase in the percentage of people in a country who are willing to pay higher taxes to protect the environment. There are some exceptions. Finland, for example, has pretty high gross national product but is very unwilling to increase taxes. The Netherlands, on the other hand, has about the same gross national product as Finland, but the people in that country are very willing to increase taxes to protect the environment. And of course, many countries fall right close to the line, which represents our correlation, like the United States, with a high gross national product per capita and kind of an average willingness to increase taxes to protect the environment. The table on the right shows the gross national product plotted against the sacredness of nature, the percentage of people in a country who believe in the sacredness of nature. And here we see as the gross national product increases, there's a decrease in the percentage of the country believing in the sacredness of nature. The graph on the left shows us a positive correlation, the one on the right a negative correlation. Looking at the table on the bottom, we can see that the correlation coefficient between willingness to pay environmental tax and gross national product is about 0.67. It's positive and strong. Remember, it can be no higher than 1, no less than -1. The correlation between GNP per capita and the sacredness of nature is -0.53. Again, a reasonably strong correlation and negative, consistent with the graphic on the right. Well, how does correlation work? You can see on the slide that I've drawn How does correlation work? You can see on the slide that I've drawn two lines on each graphic. The vertical lines represent the mean of gross national product. The horizontal lines represent the mean of the percentage of the people favoring environmental taxes and the percentage of a country favoring believing in the sacredness of nature. So this divides our plots into 4 quadrants. Everything to the right of the vertical line is above average of the gross national product. Everything to the left of the vertical line is below average below the average gross national product. Looking at the horizontal line, everything above the horizontal line is above average on both of the dependent measures, the environmental tax and sacredness of nature measure, and everything below that horizontal line is below average on those measures. The shaded areas represent the diagonals, and they show that in the example on the left that there's a lot of cases in that upper right quadrant and the lower left quadrant. And what that means is that's consistent with a positive correlation. That is, scores that are above average on X tend to be above average on Y, and scores that are below average on X tend to be below average on Y. The graphic on the right reverses that. In those two colored in quadrants, cases that are below average on X are above average on Y, and cases that are above average on X, or gross national product, are below average on Y. The trick with correlation coefficient is how to take this concept and this information and measure it and come up with that one summary statistic, Pearson's correlation coefficient. Let's look at an example and plot this example in different ways and then develop a statistic that we can use called Pearson's R. In this example, we've got two scores. We've got people who take a math test and a verbal test. You can see that person number 1 had a score of 36 on the math test and 35 on the verbal test. And you can just go through and see the pairs of points, and I've plotted them just to the right of that table. In the plot, you can see that the relationship appears to be positive. That is, the trend of the points is to go from the lower left to the upper right, consistent with a positive correlation coefficient. So I'm going to take these numbers now, and I'm going to calculate the mean of X and the mean of Y, and then I'm going to plot each of these points as a deviation from the mean of X and a deviation from the mean of Y. This plot, which you can see down on the lower left, looks identical to the one in the upper right. The only difference is that where our plot begins, that kind of point where the axes cross, is now in the center of the points because I've centered each point around the mean. This gives us our 4 quadrants. Everything to the right of the vertical line is above average on the math score. Everything above the horizontal line is above average on the math score. And you can figure out the other relationships. The last thing we can do here is, instead of just plotting the deviations of each score from their average, we can also take those deviations and divide them by the standard deviation. Now, this, you should remember, is our z-score. By calculating z-scores and plotting them, we're taking advantage of the situation where a z-score takes a variable with a particular metric and distribution and converts it to a new metric that has a mean of 0 and a standard deviation of 1. This allows us to compare any two numbers even if they're measured on different numerical scales. For example, the situation I described earlier, where we had distance measured in miles and distance measured in kilometers. If we're measuring the same distances, obviously these two variables should look the same when converted to z-scores. They should be identical. And in fact, this plot here, all 3 plots, look the same except for the scale of the variables. The first one, raw data. The second one, the points measured as deviations around their mean. And then the third one, the points measured as z-scores and plotted. So let's figure out how to turn this into a metric and into a statistic. The first part of our statistic is this mess up here on the upper left. The sum of the quantity of x minus x bar times the quantity of y minus y bar. That's called the covariance. And that number, that quantity, really drives Pearson's R. It gives us a lot of really good things about the positive aspects of Pearson's R. It's going to give us direction. It's going to produce a number that's either negative or positive, and it's going to give us magnitude. It's going to be bigger when there's more of a correlation or association between two measurements. So how does that work? Well, if we look in the area of the graph I labeled quadrant 1, you'll notice there when we have deviations of x from x bar that those deviations have to be positive. You'll also notice that if I have deviations from y from its mean, y bar, those deviations have to be positive as well. Why? Because x and y are both above average compared to the x bar and y bar. When we multiply two positive numbers together, obviously they're positive. Well, now look down in quadrant number 3. Here our deviations are negative. That is, x minus x bar will produce a negative number because whatever x value is in that quadrant has to be below average on the x-axis. Same thing for y. Whatever y value exists in that quadrant number 3 is going to produce a negative value when we subtract the mean from it. And when we multiply a negative number times a negative number, we get a positive number. So when our cases mostly fall in quadrants 1 and 3, remember that's consistent with a positive correlation, then we should get a large number, so there's our magnitude, and it should be positive. Well, switching over to quadrants 2 and 4, you can see here that the product of these two deviations have to be negative. In one quadrant, x is going to be below average but y above, so 1 is negative, 1's positive. And in the other, that reverses with 1 positive and 1 negative. And we know when we multiply a negative number times a positive number, we get a negative number. So if our points, our scatter plot, shows points that concentrate in the quadrants 2 and 4, that's consistent with a negative correlation. And the more points that fall into those quadrants, the greater the quantity. That is, that covariance will get larger the more cases fall in those quadrants. So again, we're going to get direction and magnitude. Now, this isn't a particularly good measure because, first of all, it's sensitive to scale. Measure something in miles, measure something in kilometers, I will get a different covariance by this measure. Also, it's sensitive to sample size. If I increase the number of cases, so I'm doing more summation, then that number is going to get bigger, not because there's a greater correlation, but simply because I have more cases. So we're going to make two adjustments to this covariance. But remember, it's really this quantity, this covariance, that drives this whole statistic. It provides direction and magnitude. The first adjustment we're going to make is to get rid of the scale of the measures. And to do that, like we did in the slide before, we're going to take those deviations and divide by the square root and divide by the standard deviation of their respective variables. That is, we're going to take each point and convert it to a z-score before we multiply them together. This puts our distance, kilometers and miles, into the same metric. Same thing with this math test and verbal test. Maybe the math test was out of 200 points and the verbal test out of 10 points. How do we compare those two measures if they're not standardized? It's very difficult. We could convert them to z-scores first to make them relative measures, measures relative to their means, and then be able to assess, how they relate to each other. Second adjustment, and really the final one we need to make, is to average this number out to account for the number of cases. Now you'll notice I'm not really averaging by n, but n minus 1. So again, we're averaging by the degrees of freedom of this particular statistic. So let's put this all together. In that computer output at the top, I went and calculated all the quantities I need by hand. I have my math score and my verbal score. I have the z-scores for math and the z-scores for verbal. And then I have the product of those two values. So you can see that person number 1 with a score of 36 was below average on the math score, and with a score of 35 was below average on the verbal score. And when I multiply those two negative numbers together, I get a positive number. And I do this for everybody in my data set, for all 10 cases. Calculate the different z-scores and then the products of the z-scores. And finally, I divide by 8 minus 1, the number of cases minus 1. And I get a correlation coefficient of 0.63. This correlation coefficient is consistent with the graphic. That is, the graph shows that as math scores increase, they tend to be associated with high verbal scores, and that low values on the math score are associated with low values on the verbal score. So it's a positive correlation. It's also a reasonably strong correlation, 0.63. 0 would imply no correlation. 1 would imply a perfect correlation, that math scores perfectly predict verbal scores. So this is a very strong correlation coefficient. Here's what some computer output looks like. I listed the variables math and verbal above, and then I produced some summary statistics. I like looking at the summary statistics. I always think it's useful to know what the mean is and what the variability or the standard deviation is. Down at the bottom is really what the output looks like from a computer package, and it just shows us our little correlation matrix with our correlation here with 4 places of precision of 0.6264, which is consistent with my hand calculations of 0.63. There's other ways to calculate Pearson's R by hand or with a calculator. I'm hoping you don't need to use them, but I'm providing the formulas here just for your information. To understand these formulas, you have to understand that there's a symbolic way of expressing deviations from the mean. When you see a small italicized x or a small italicized y, that typically implies the deviation form, or x minus x bar and y minus y bar respectively. So we look at this table at the top. Here's the things that we need to calculate. We need the mean of x and the mean of y so we can calculate the deviations. Then we're going to calculate the products of those two deviations. We're going to take each x value and square it and each y value and square it, and then sum those values up. There is a little bit of error involved in here, and there's a fair amount of calculator work. Well, we need the means, so that takes a bit of time to calculate. And then we'd have to calculate all the deviations from the mean. That's the downside to using this formula. The upside to this formula is once we get those quantities, sum of xy, sum of x squared, sum of y squared, that we can plug them into the formula and very easy with a calculator get our final correlation coefficient of 0.63. So the pro of this particular way of calculating the correlation coefficient is the formula is easy. The downside of this is that getting the pieces we need, the numbers we need to calculate the correlation coefficient to plug into this formula, are a bit difficult to get. There's another formula that we can use, and again, sometimes I feel like the statistical gods mock us. Whenever they give us something, they take something away. So if we look at the formula down below, you'll see that that's actually quite a difficult formula to use if you're using a handheld calculator. It's just very difficult to keep all the quantities separated and to get all the subtractions and the multiplications done properly. That's the downside of this particular method of calculating the correlation coefficient. The upside of using this is that we don't need to calculate the averages for x and y, and we don't need to calculate the deviations. So there's a lot less calculator work. There's less keystrokes involved in using a calculator to calculate this correlation coefficient than the other one. But then we have this horrendous formula that is actually quite difficult to use with a handheld calculator. At the end of the day, I hope you really never have to use either of these two formulas, because when you learn how to use Stata or SPSS or SAS or SDA, you can have the statistical application calculate this number for you as long as you understand what the number means. And to understand a correlation coefficient, I encourage you to go back and look at that original z-score formula. That z-score formula is what I would call a heuristic or pedagogical formula. It's not the one that we would use to calculate this by hand. Again, too many means, too many deviations, too much calculator work. And that particular formula has a bit of rounding error in it. Rounding error gets compounded with large numbers of cases, and that formula is really not good with rounding error. On the other hand, if we understand the pieces of that formula, what's the numerator? The numerator is the covariance. The covariance drives the whole statistic, giving us direction and magnitude. Then we're just going to create z-scores first to get rid of the scale issue, and then we're going to divide by n-1 to get an average value. If you understand that conceptually, then no matter what computer package you use to calculate your correlation coefficient, you should be able to interpret it intelligently. We're going to pick up with some additional issues with correlation, show you shapes of distributions, and take on tests of significance in other videos. As always, if you have any questions, please let us know. Talk to us in class, send us some emails, and we'll try to answer all your questions.